Hello, my name is Mejias from CANTENE, and I'm here to talk to you about our article From Theory to Practice, Implementing FDS Developments into Streamline Fire Safety Assessment. First, two words about us. CANTENE began as a startup at the age of incubator of the Polytechnico di Torino, and we specialize mainly in CFD analysis, risk analysis, and evacuation modeling. Returning to the topic at hand, let's enter in context by establishing the link between what we do and FDS. Fire safety engineering was initially based only in prescriptive codes, so the designs had to fit legal regulations and standards, regulations that sometimes could be restrictive with materials or dimensions. This has been changing in the last 10 to 25 years with the introduction of performance-based codes, which require the buildings to match some performance criteria to ensure the safety of the users. But you need computational tools to simulate a fire scenario to ensure this criteria in most of the cases. And here's where FDS fills the gap, being an open source software in continuous development that simulates a wide variety of fire scenarios. Among the updates in the last 4 years, we particularly remark this one where the tunnel preconditioner was introduced and the 6.8 where the unstructured geometries were introduced. Continuously developing FDS also means issue solving. In particular, some pressure issues have been linked to the low Mach number assumption. According to Wren and Baum, if the flow in your domain is below 0.3 Mach, you can divide your pressure into a background pressure and a perturbation pressure. This has many advantages, as you can simplify your calculations and you can unlink the time step from the speed of sound. And it also has some inconveniences, as the pulsation of the fire introduces the volumetric flows inside your domain that reach infinitely fast the boundaries. This in a small or relatively small domain is not a problem, but when it comes to the simulation of long tunnels, it can introduce instability into your simulation. But there are some ways to mitigate this effect. And the first one has been introducing relief open vents. So we will introduce small opens from one cell size dimension, which will act as relief valves. So the volumetric flow introduced by the pulsations would be discharged or entered through these small opens, enhancing the stability of the model. Also, the FDS developer have developed this new solution through the tunnel preconditioner. Here, using a 1D model, they calculate the pressure inside the whole tunnel and then use these values with all the meshes of the simulation to enhance the convergence and stability of the pressure values across the tunnel. Other than this pressure management, we will also analyze the meshing methodology. So if you use only one-dimension meshes, or if you use meshes that are coarser away from the fire and finer closer to the fire, and the flow rate management. So modeling using the action of the jet fans to find the flow rate inside the tunnel, or simply imposing the volumetric flow in one of the boundaries and not considering the jet fans or the roughness of the tunnel. And the scenario where we will use it is the Memorial Tunnel. The Memorial Tunnel is an 854 meters long tunnel that is located in West Virginia that was decommissioned in the 80s and then was transformed into a ventilation testing facility. In this facility, they did a series of 98 fire tests with more than 3 HRRs using different types of ventilation, among them different types of transversal, semi-transversal, longitudinal, and even some natural ventilation tests. So we're going to use this test in specific where the fire is positioned 238 meters from the south portal. The HRR is of 10 megawatts, and we have a total of 15 fans in 5 sets of 3. So during the simulation, this will be the HRR, and here we have the activation of the jet fans. In simple words, there will be 2 sets of 3 of jet fans activated through most of the simulation. So from 5 minutes up to the end, there will be 2 sets activated. These are the tests that we are going to do. So first of all, we will do the test present in the validation guide using the uniform 0.28 meter cell size mesh, the Tuni preconditioner, and the action of the jet fans. Then for the second test, we are going to change the Tuni preconditioner and use the relief open vents across the tunnel. For the third test, we are going to change the mesh, introducing a 0.2 meters cell size mesh close to the fire and a 0.4 meters mesh away from the fire. And in the last case, we are going to stop using the jet fan action and the roughness and make an input of the volumetric flow rate of the first scenario into the north portal. So here are the results of the first scenario, that is just as in the validation guide of FDS. Here we can see first in the volumetric flow rate being the black line, the experimental measurements, and the red line, the simulation results, that the simulated volumetric flow is always lower than the one measured in the field. This other graph is the temperature contour across the tunnel made with the temperatures placed in the ceiling of the tunnel. Here we can see that the temperatures of the simulation remain shorter to the ones of the experimental measures. Here we can compare them in slices at 4, 6, and 8 minutes. And we can see that here the black line represents the experimental measurements. The 50 degrees remains a little bit further down the tunnel towards the north portal when compared to the color change that represents the 50 degrees in the slices. We are also including the visibility as it's an important output for us. And we can see that it moves 200 meters away from the fire towards the north portal, and a maximum of 500 meters. Now, in the second scenario, we change the Tuni preconditioner, so we stop using the Tuni preconditioner, and we add the relief opens across the tunnel. Here we can see that when it comes to the volumetric flow rate, the change is very small. So being the blue, the new simulation, and the red line, the past scenario, they are mostly the same. Instead, the temperature contour across the tunnel, let us see that now the temperatures across the tunnel at the ceiling go further towards the north portal in the case of the new scenario. This can also be seen here in the slices where the 50 degrees matches better in the first graph, but then it starts matching with temperatures that are higher, so here maybe 60 or 70 degrees, because now the temperatures of the simulations are going further when compared to experimental measurements. Also, the visibility drop advances further towards the north portal. In the third scenario, we will change the mesh for meshes that have 0.2 cell size in the vicinities of the fire and 0.4 away from it. Here we can see that in the natural ventilation part of the simulation, so in the first 5 minutes, the results are the same. But then when the jet fans are activated, there is a drop in the volumetric flow in the new simulation. Also, this is reflected in the temperature contour, as we can see that the temperatures after the activation of the jet fans in the third scenario arrive further towards the north portal. Here in the slices, we can see that the situation is similar to the one appreciated in the second scenario. Still, at 8 minutes, we can see that there is more, that the slice has higher temperatures, and that the visibility drops closer to the north portal. Here in the fourth scenario, we stop using the jet fans and we just impose the volumetric flow from the first scenario into the north portal of the simulation. We don't show the volumetric flow because as it was imposed, it makes no sense to show it anymore. But we can see that the temperature contour reaches further to the north portal. The temperatures are higher, closer to the north portal. And it makes sense, as in the slices we can see that the temperatures close to the roof remain higher through most of the 3 slices that we are shown at 4, 6, and 8 minutes. Also, the visibility doesn't seem to be controlled anymore. I mean, the smoke seems to when it comes to the simulation time, we can see that the first scenario and the second scenario took roughly the same amount of calculation time. This means that using the tunnel preconditioner or using the relief open vents doesn't have really an impact in the simulation time that we use. But changing the meshes from uniform meshes to the meshes that we use of 0.2 and 0.4 reduces the simulation time roughly to the half, having also a price in the accuracy of the simulation, as the jet fans are not simulated with the 0.2 but with the 0.4 mesh. At last, changing the way we calculate the flow inside the tunnel, so using the jet fans or not using them and making an input of the volumetric flow, changes also the simulation time, but it also has a drop in the precision of the simulation. In the end, we can conclude that from a numerical point of view, the tunnel preconditioner is a step forward for the FDS code because it manages to provide stability for the simulations without the need to modify the model in any way. Still, from a fire safety perspective, it is normally preferable to have some reassurance that the simulation results that we are considering to make the safety evaluation for the users overestimate to a certain degree the conditions inside the tunnel. And this is the main reason why we prefer in this case the results obtained in the second and third scenario, as they remain close to the experimental results but introduce some margin to the safety evaluations. Still, this evaluation is made for this scenario. And for other cases with bigger HRR, or even other cases present in the validation guide, the trend could be different. So this is why we propose that as a future development, more of this sensitivity analysis should be done so that we fully understand the consequences of our simulation modeling decisions, so that we manage to obtain results that are safe for the users without entering into exaggerated overestimations of the conditions inside the tunnels. And at last, I would also like to to thank FDS for all the material that they have available in the GitHub and everywhere, and also the software, because it made a lot easier the development of this small work. Thank you very much for your attention. It was a pleasure.
Hi, can you hear me?
Yes. Now I can hear you.
Welcome.
Thank you.
I had a question. When you said that one of the more significant differences when you changed the mesh resolution to the 0.2, 0.4 option, what was the difference in cell count, total number of cells in the simulation?
Yeah, it was reduced a lot, but I think I don't say it explicitly, but I think it was a factor, the cell count, but probably it was also the fact that the jet fans now were inside the coarser mesh. So the speed of the jet fans, I think, it was the one that was defining the time step. So being inside a rougher, and coarser
larger
mesh,
cells.
yeah, the time step will be a little bit longer.
Yeah. Okay. Let's see. Do we have any questions in the room, Kevin?
Hi, Jesus. Very good talk.
Hey. Thank you.
I've noticed in running these simulations that they can be very grid dependent. So for example, the extent of the back layering is still, more of a function of the grid size than we would like. So if you were going to continue doing work in this area, you might want to try a grid convergence study, say with 40 centimeter cells down to 20, down to 10. I know doing 10 centimeter cells in the tunnel is very difficult, but that's one thing that's on my plan, is to try to see if I can reduce the grid sensitivity of the extent of the back layering. This is just a suggestion. It's not a question, really.
No. I know. You are the developer. You know this code way better than me.
Yeah.
No, I saw also another grid study from Matthew Wilson. Maybe refer to the tunnels in.
Yes.
Yes, I think you know which one.
Right.
And they did some grid sensitivity, and also they had the same conclusion that.
Yes. It's very sensitive to the grid.
Yeah. I know, but it's hard to take everything into account. But you know it better than me, so.
Yeah. Right. But one thing to investigate might be the boundary conditions for the momentum equation near the ceiling. That's something that we're interested in. For example, looking at roughness or the velocity slip conditions. It would be very interesting if you were going to continue this work to focus on the grid sensitivity.
Because the thing with roughness is that a lot of times it's, now that I'm working with this consultants group, that I'm a consultant, sometimes you don't really have a lot of information about it. You end up trying to use like a value, an average value or something like that. So it's one of the terms that you would like to don't put too much focus on it. I think right now, as of today, that's the idea I have on it.
Well,
you need it. Okay.
Yeah, one of the ways that we estimated the roughness of the Memorial Tunnel was we looked at the volume flow through the tunnel, as you showed in your presentation, and we adjusted the roughness to match the volume flow in some of the experiments. It's not a perfect match, as you showed, but we had some idea of the roughness based on looking at the volume flow. Yeah.
No, you also did the volume. The cold tests with the different amount of jet fans. So I think I didn't stress it enough saying that it's a great work. The validation test, it has a lot of work into it, what you did. But it's kind of difficult to match all the numbers.
Yes. But good job. Thanks.
Good job to you too.
Anyone else before? No. Okay, good. All right, sorry to interrupt your clapping. I was making sure nobody else had a question. Thank you. Thank you.
Thank you.